Alrighty, this lesson here, we're starting the last bit of the motion stuff, and it's to do with work and energy. So there's, I think, 3 lessons on this. So work and energy, first of all, we're going to look at work. So from ideas that we have, if you think about work when you go to work, then there's some effort involved. Now, you're not going to hold your job for very long if you don't have some result or some output. So there's some sort of result / output, achievement, whatever, blah, 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 however you want to. But there's something has to happen, all right, when you work. So you put in effort and something happens. So the effort's the first missing word. So if we think about like pushing a wheelbarrow, that's the example there. So if we're pushing a wheelbarrow, what do? We apply some force, and what happens? The wheelbarrow moves, so we got some distance that gets covered. All right. So if then we use some common sense here, which Edison said is not all that common, but anyway, not to worry. The work done combines those 2 things. Work equals, this in your notes, work equals force times distance. All right, and so normally we see that written as W equals Fx. And the unit is joule, after joule. So when you become a famous physicist, maybe you can get a unit named after you. All right, so find the work done against a frictional force of 7 Newton if the fridge, I assume that's what we mean in the first bit. So we got this fridge on the floor there, and here's you. Pushing the fridge, and there's a frictional force of 7 Newton, so if the fridge moves this way where you're pushing it, so friction is a resistive force acting that way of 7 Newton. It's a bit ugly, but anyway, let me rub that out and write that again. 7 Newton. Now it says here, kept at a constant velocity of 2 meters per second. All right, so constant velocity of 2 meters per second, all that tells us then is that the acceleration is 0. And from Newton's second law, you'll all say, oh, because the acceleration is 0, the sum of those forces must be equal to 0. So if there's a 7 Newton resistive force, then you've got to be pushing the fridge with 7 Newton as well. Now, the thing is, you need to move your fridge, and you're going to move your fridge this 10 metres here. And so the work that you do on the fridge, work is Fx. So the work you do on the fridge is 7 times 10, which is 70 joule of work that you do. All right, so that's pretty simple, pretty straightforward. So just the force applied times the distance it moves. All right, graphs. All right, graphs. So if we have a force distance graph, so force distance graph, got force on the vertical axis, distance on the horizontal. And in this case, we might have force that's changing, and that there's a curve. The question is, how do we calculate the work done? So a way that we can estimate that is break this curve up into a series of rectangles. So I go to rectangle there, that one there, and then I make another rectangle next to it, that one there, that one there, and so on. And then I make a whole bunch of rectangles like that. So each rectangles, and I'll make them all the same width, just out of convenience, and if I make them all the same width, the width of x, and then the height of them is some force, and I'll do that italic F. So you have a series of rectangles, all of them have an area of F times X. So we could get an approximation there if we added all of those up. Now, when we do that, we do get an approximation of the area underneath. But, of course, the area underneath, each of the rectangles has an area of F times X, yeah? So the area is F times X. But also from what we did down here, over here, the work is F times X also. So each of those little ones is a, so if we add them up, in your notes it says, so if we add them up, we get that the sum of all those little F times X's is the area, and of course it's probably the work. Well, it is the work that's done. Now, the mathematical way of doing that, there is a mathematical way, it's called calculus, and calculus actually does better than approximation. Calculus is more accurate than that. It gives us the actual area, and it's in calculus forms. It's the integral of fx dx. So we haven't done calculus yet in maths, but we will be. And so that is the area. And of course, that is also the work done, which I've already said. So the thing is, work done is the area under an fx graph, force distance graph. Now, the good thing is that we don't, for a curvy one like this here, you would need to know what the equation of that curve was, and that's where the fx bit is. Fortunately for us, what we're doing, we're not going to worry about anywhere curvy ones, just ones that have straight lines that we can break up. So let's have a look at a couple of examples. Okay, so let's look at this example. Find the work done in the following cases. There's going to be two examples. So from what we've just talked about, we've got a force distance graph here. So what we've just talked about is that the work is equal to the area underneath. Now, the area, we can break it up, and there's a whole bunch of different ways we can do it. If you know what the area of a trapezium is, you can use that off the top of your head, or you can go, all right, I'm going to break that into a rectangle there like that, and that rectangle area there of that is 4 times 10, which is 40. And then I'm going to break this up here, this triangle here, and the area of the triangle is a half times the base, which is 10 times the height. So where are we going from 4 up to there, which looks like that's 9. So 5 9s are not what we're after, because that's 9, all right, but we're going from here to here, so it's 5, not 9. So anyone who's picked that one up, hopefully you did. So that's times 5. So half of 10 is 5, 5 5s are 25. So the work done then is the area, and the area is 40 plus 25. So the work done here would be 60 joule. Alright, so however you want to break it up and calculate the area is fine, it doesn't matter. Alright, example 2. Alright, so sample 2, same deal. Got a force distance graph, and we want to know the work, and so the work is the area. that we're looking for. So split it up however you feel like it. There's a whole bunch of ways. So there's that there. Bring that there. So what's that? That's area there is 10 times 3, 30. And I make a little triangle here. And so that area there is a half times the base. So we're going from 3 to there. So 3 to 5, that's 2. And then we're going from 6 to 10 there. That's 4. And so that area there is 4. And then, of course, that then leaves us with this orange one down here. And the area there is, well, we're going from 3 to 10, 7. And we're going up 6. So 42. So our area, 30 plus 4 plus 42, is, I think, 76 joule. All right, and if you look in the notes, the notes gives you a different answer because I've made an error in the notes. So in the notes, you notice the last bit there, I've got 5 times 6, but from there to there is 7, not 5, so I've made a mistake in the notes. So in the notes, that's a 5 there, but it should be a 7. So 76 joule, not what it says in the notes. All right, so by the time you get to there, maybe I fixed it, maybe I haven't. So just keep aware of that. So answer is 76 joule. All right, now the last bit is the work is actually a scalar. So it's not a... all right, so as I was saying, work is a scalar. But force isn't, and neither is displacement. So force and displacement are vectors. So what have we got? So we've got something that maybe moves in that direction, but we may, say, be applying a force in that direction. All right. And so X is in that direction. So we kind of think they're in different directions. So how do we actually get the work done? Well, this force that's there is actually doing two things. One component of the force is moving in that direction. The other component of the force is trying to move it in that direction. So when we are calculating the work, we are interested in the green by the black X. All right, so what do we need to know if we're going to calculate that green? Well, if we're going to calculate that green, we need to know this angle in here. All right, so in your notes in the second bit there, so what we need to take the component of the force in the direction of the displacement. All right, there's a little bit of a abbreviation that I use for direction, because I'm too lazy to write all those words. All right, so in your notes, a couple of lines there in your note. In your notes, so work is component of force in the direction of displacement times the distance that we move. All right. Now that's all a bit long-winded. So what is this green one here? Well, this green one here is adjacent to the angle. So this green one is actually F cos theta. So in the symbols then, we can write that work is equal to Fx cos theta, where theta is the angle between, that's the word missing in your notes, between F, or the force, and X. Alright, example. Alright, so here's our example. Find the work done by the force if the distance moved is 6. Alright, so as I said, if this is a box and we're dragging it along the table, it's going to move horizontally along the table. So part of the component is trying to do that, and the other part's trying to lift it up, and then there'd be weight holding it down. So what are we interested in? We're interested in it moving from here to here, which is 6 metres. So again, it's the green force, and so the work is Fx cos theta, which is 10 times 6 times cos 60 degrees. And when we put that in our calculator, you get, it's a bit ugly, you get 30 joules. So there's 30 joule of work done moving that box 6 metres along the table or whatever by that force. Alright, problem set number 20. I'm getting down. So there's a couple of videos, have a look at those videos, and also if there's anything that you ain't sure of or need me clarifying, be sure to ask.